Hello students, welcome back. I hope that you are following this lecture from starting. We discussed about solids and the types of solids, and then we discussed about the classification of crystalline solids particularly, and then we discussed about the concept of crystal lattices and unit cells, and we also discussed about the various types of unit cells we have, and we also calculated the number of atoms belongs to each unit cell effectively. Now we are going to discuss about a very important and interesting part of the solid state, that is close packed systems, close packed structures. So we know that in solids the particles are arranged in three-dimensionally. So in how many ways we can arrange the particles in three-dimensionally and how we can do that. So to know about all these things, let's start. So now we are going to learn about close packed structures. So this particular part is very important and you need to concentrate a lot, because if you don't concentrate, you don't understand most of the things. So you have to be very attentive in this particular part to understand the things clearly. Okay. So close packed structures. So as the name suggests that these are the structures which are found by the close packing of the atoms. Okay. So here what I am doing is I am packing in a very close fashion, so that the empty space, or I can say void space, is I am making minimum and I am utilizing most of the space. So that is why the structures which are found by the close packing are known as close packed structures. So in this close packed structures, the particles are treated as hard spheres of identical size. Okay. So all the particles are identical and they are all hard spheres. Okay. Yeah, here you can see there is one blue layer which is arranged, and above the blue layer there is one more layer is arranged in which is differentiated with another color, and above that there is a green layer is arranged, and above that there is a blue layer. That means it's a repeating, right? So first blue, this is blue and this is more color. That means the second layer is having a different arrangement from the first one. So that's why they are shown with the different colors, and above this one there is one more green layer which is having even different arrangement than these two layers, and above the green one we are repeating the blue layer. So it is a three-dimensional closed packed arrangement or closed packed structure. Okay. So let's discuss more about it, or let's understand more about it. Yeah, here also which is shown is a close packed structure. So the packing of these spheres takes place in a such a way that they occupy maximum available space, and hence the crystal has maximum density. So that's why these structures are known as closed packed structures. Okay. So let's see in how many ways that we can arrange the particles in one dimension, 2 dimension, and in 3 dimensions. So first we will understand, so to understand the packing, how it is done, first we need to understand one dimensional packing. So after one dimensional we discuss 2 dimensional packing, and from the 2 dimensional we will go to the 3 dimensional packing, which is more realistic. Okay. So first is one dimensional packing. I have given you a set of spheres. Say suppose I have given you 7 or 8 spheres and I asked you to arrange them in row in one dimension. So in one dimension it does not have any freedom. Like if you are putting one sphere here, then you need to put the other sphere beside that. Say suppose here I am arranging them in x axis, along x axis. So this is the only possible arrangement in one dimension, right? You don't get any other arrangement. This is the only possible arrangement. So if you observe here, if I take this sphere, it is touching the two, one on the left and one on the right. Let me point out. Here I am concentrating on this sphere. So this sphere is touching this one and this one. Okay. So this sphere has 2 neighbors. Similarly, this sphere also has 2 neighbors, and this sphere also has 2 neighbors. So in one dimensional packing, the coordination number is 2. Here coordination number is the number of nearest neighbors is called coordination number. So if I take any particular thing, any particular sphere here, and that is having a coordination number 2, okay. So because it is having 2 nearest neighbors, only 2 are touching with each one, so that's why it is having a coordination number 2. So this is about one dimensional packing, which is the simplest of all. So let's move to a bit complicated packing, that is 2-dimensional packing. So 2-dimensional packing, there are two ways you can arrange in 2-dimensional spheres. So the spheres you can arrange in 2 different ways. So let's see what are those 2 different ways. Okay, so here I am showing one of the way. Here this is the 1-dimensional packing. The spheres are arranged in this fashion, and here since I need to arrange in 2 dimension, what I am doing is I am placing a sphere which is exactly below this one. I am placing this one exactly below this one. So the second row is exactly identical to the first row. So that's why I am giving the same. See, if I call this type of arrangement is A, this layer is A, this row is A, then the second row, which is exactly similar to the first row, so that's why this is also A, and this is A, this is A, okay. So here all the rows are identical, and if you join the corners of the 4 adjacent spheres, you will get a square, or even you can take like this. So here we are getting a square, right? So that's why this is known as square close packing. Square close packing, and which is simple. So you are taking a 1-dimensional row, and you are placing the rows below and above that in an exactly similar manner, and you are getting a square close packing, which is a simplest 2D packing, okay. So let's go to the other 2D packing, which is a bit different from this, and which is a bit difficult from this. So 2D packing, the second way of arranging them. So here I am taking the first row, that is A is my first row. What I have done here is, instead of placing the spheres exactly below, I am placing in the depressions. Here let me make you understand. So if I take 3 spheres, I arrange them in a row. Now what I am doing is, instead of placing the sphere directly below here, I am placing here. Like this, okay. So this is A. So here I am placing this sphere in the depression of this one. I am placing this one in the depression of this one. So if you see, this layer thus form layer B is different from this layer A, okay. That's why I have given a different name. So this is layer B and this is layer A, and layer B, if you place the spheres in the depressions, you will get the layer exactly similar to A, right. So here A, these 2 rows are similar and these 2 rows are similar, okay. So it is a AB type, okay. So which is a hexagonal close packing. So how it is hexagonal close packing, that you need to understand here. So before we have seen square close packing, but this is hexagonal, because if you take, see, these 6 spheres, and if you join the centers, you are getting an hexagon. Before you got a square, but now you're getting an hexagon, and that's why this type of packing is known as hexagonal close packing, okay. So in 2-dimensional, 2 types of packing is possible. One is square close, another is hexagonal close packing, okay. So let's move to the more realistic case and the real case, that is 3D packing, okay. So now we started with the simple packing and we are moving towards the complex packing. So now we are going to discuss about 3D packing. So 3D packing, 3-dimensional packing. So 3-dimensional packing you will get from 2D packing. So before, what we have done, we have arranged one layer, right. So if I place one more layer above this and one more layer above like this, if I place like this, I will get a 3D packing, simple. So 3D packing is basically derived from 2D packing. by placing the layers one above and below the other. Okay. So let's see now how many ways, how many different 3D packings are possible. So they can be obtained by stacking two-dimensional layers one above the other, which I already said just now. So total 3 types of 3D packings are possible. Total 3 types of 3D packings are possible. 3 types of packing is possible. Let's see what are those 3 types. So one type is from two-dimensional square close packed layers. Okay. So we have seen square close packing, right? So from two-dimensional square close packing, you will get 3D. This is one 3D packing, and other is from 2D hexagonal close packed layers, right? So from 2D hexagonal close packed layers also you will get 3D packing, but here this is one type. This is one type 3D. This is second type, but here in this 2 types further possible. Okay, so total we have 3 types. So one is placing the second layer above the first layer. Okay, so first layer you have placed and placing the second layer above the first layer and placing a third layer over the second layer. Okay, so here first we have placed one hexagonal packed layer, close packed layer, and that is the first layer, and above that we are placing a second layer, and above that we are placing a third layer. Okay, so here 2 different types of arrangements are possible, and those 2 different types of arrangements we will going to learn in our next slides. So be careful and try to be attentive to understand these things. So here what you will get is covering tetrahedral voids and covering octahedral voids. So we will discuss what is tetrahedral void and what is octahedral void. So let's start with the packing. Okay, 3D packing. So first 3D packing is from the square 2D packing. From the 2D square packing. So yeah, from 2D square packing, let's see how you will get 3D. So here if you see, this is layer, the first layer, this is the first layer, that is a square close. So what are you doing is exactly similar layer you are placing below, and exactly similar layer you are placing below, and now you got a 3D packing, and this 3D packing is AAA type. That means if I call the first layer as A, the second layer which looks exactly like the above layer, so it is also A. So A, all layers are exactly similar. So this is a AAA type of arrangement you will get. Okay. So this type of crystal lattice thus formed is a simple cubic lattice. A simple cubic lattice because it is a simple cubic lattice and its unit cell is primitive cubic unit cell. Primitive cubic unit cell. Like if you join the corners of these 8 spheres, you will get a primitive cubic unit cell. Okay. So this is one type of 3D close packing, which is the simplest 3D packing, but less efficient. So now let's discuss the other 2 3D packings which are more efficient, than this, and which are also more complicated than this. So from 2D hexagonal packed layers, the 3-dimensional close packed layer can be generated placing layers one above the other. So now placing the second layer over the first layer. So first layer what we have is a hexagonal close packed layer like this, that we already discussed, the hexagonal close packed layer. It will be like this, right? So this is my first layer. So what I am doing is now I am placing the second layer over this first layer. So let's see how I can place it. Place a similar layer above the 2D hexagonal packed layer A such that the spheres of the second layer are placed in the depressions of the first layer. That means what you are doing is, say this is your layer A. What you are doing is, now you got a depressions like this. See, this is a depression, and this is a depression, this is a depression. This is a depression and this is a depression. So place the spheres of the second layer in the depressions of the first layer. That means you are placing 1 here, you are placing 1 here, like this. Okay. So if you place like this, you will get a layer which is quite different from the first layer. Okay. So that's why let's call the second layer as B. Okay. So first layer which is at the below, that is layer A, and above we have a layer B. Yeah, which you can understand clearly here. So this is a very important thing. Most of the things that I am going to discuss from this picture only. So that's why please be attentive and observe the things clearly. So this is my first layer A. Okay. But the second layer, which is shown in the dark red colored spheres, is my second layer, which is arranged differently from layer A. So that's why this is my B layer. Okay. So here if you see, I arrange the second layer spheres in the depressions of the first layer. So this is a depression of the first layer, and I placed here a second sphere of the second layer. So this is, so in this way I arranged the spheres of the second layer. Okay. But what you are observing here is there are T's and O's, right? T and O. So T is tetrahedral void, O is octahedral void. Okay. What is void? Void is an empty space, right? So empty space within this crystal are known as voids. So we have two different types of voids. One is tetrahedral voids, another is octahedral voids. So let's first discuss about tetrahedral voids, and later we will discuss about octahedral voids. So let's see the tetrahedral voids first. So these are tetrahedral voids. Okay, I'll use a different color. Let me use green. So this is a tetrahedral void. These, and this is also tetrahedral void. These are also tetrahedral void. So let me use some other color, different color for octahedral voids to make them. Yeah, these are octahedral voids. Okay. So let's see how a tetrahedral void is formed first. So let's concentrate on this. Okay. So tetrahedral voids. So wherever a sphere of the second layer is above the void of first layer, a tetrahedral void is formed. So let's go to the picture to understand this point. See, if I take this tetrahedral layer, okay. So what I am doing here is how this tetrahedral void is formed is, this is my this is the sphere that is belongs to my second layer. I am placing this layer in the depression of the first layer, right? So the depression of first layer is like this. It is in this shape, like this. Right? Yeah, this one. So this is the depression of the first layer, and I am placing a sphere directly above this void, this depression. I am placing a sphere of the second layer directly above this one. I am placing it directly above this one. So whatever the space that is formed between these four spheres, this is one sphere, this is second sphere, third sphere, and this is my fourth sphere, which is above that. So four spheres are there, in which the three spheres are belonging to one layer, and there is one more sphere which I placed above this depression, and that sphere belongs to my second layer, like this. Okay. So if you see, if you join the corners of these four spheres, you will get a tetrahedron. I will show here. Yeah, if you see, if you join the centers of these four spheres, okay, so you are getting a tetrahedron. So that's why at the center of these four spheres, you are getting some empty space, that is void, and this is known as tetrahedral void, because this void is surrounded by a tetrahedron. Okay, this void is surrounded by four spheres, and these 4 spheres are making a tetrahedron. So that's why the name given to such void as tetrahedral void, and the green spheres are belonging to layer A and this is belonging to layer B. Okay. So yeah, you can see there are 3 spheres, blue, which are shown in blue, belongs to layer A, and this one sphere which I placed in the depression of the first layer, and this is these 4 are making a tetrahedron, and this void is known as a tetrahedral void. Yeah, you can observe here. Yeah, you can see this is the void and this is the tetrahedral void. Okay. So in tetrahedral void, you can see here these 4 particles are forming a tetrahedron. So there will be a void at the center of this tetrahedron. Okay. So this is about tetrahedral void. So let me go back, and if you see here, there are 2 types of tetrahedral voids we have. So this is one type in which we are having a depression like this, in which the apex is downwards like this, and this is also tetrahedral void, but the apex is upside like this. Okay. So yeah, this is about the tetrahedral void. Okay. So I hope that it is clear to you. The tetrahedral void, which is formed by 4 spheres, 3 belongs to one layer and one sphere will be above or below. Okay. So now let's go to octahedral voids. Octahedral voids are not so complicated, they are also easy, but if you see how an octahedral void is formed, yeah, octahedral voids are surrounded by 6 spheres, and the triangular voids in the second layer are above the triangular voids in the first layer, so that the triangular shapes of these do not overlap. Okay, this statement you may not understand, but you can only understand with this thing when I show you a picture to you. So here remember that there is a triangular void in the second layer are above the triangular void of the first layer. So let's go back and let's see that. Okay, this is an octahedral void. Why? Because you can see there are 3 spheres we have. This is one sphere in the first layer. 1, 2, 3 spheres are there in the first layer, and this one, and this one. So total there are 6 spheres, 3 above and 3 below, and these are forming a octahedral void like this. So these 3 are belongs to the first layer A. Okay, and there is one triangular void like this. This is a triangular void, right? This is a triangular void like this. Okay, and if I place the spheres like this, so that if they form, okay, this is the above, and we have a triangular void form in the second layer, right? So this is the triangular void formed in the second layer, which is like this. So there is a triangular void directly below the triangular void formed in the second layer. Okay, so there is a triangular void formed in the first layer like this and second layer like this. Okay, so this void is surrounded by 6 spheres, so that's why it is known as octahedral void, and the centers, they are forming an octahedron. I hope that it's clear to you. Let's see the pictures. Okay, here you can even understand better. See, I have 3 spheres of first layer, and I am placing the 3 spheres of the second layer, so that there is one octahedral hole formed here, right? Yeah, you can see here clearly 3 blue are below and 3 red are above, and you can see there is a triangular void this is the triangular void formed in the first layer, and this is the triangular void formed in the second layer. So the two triangular voids are just directly one above the other, and these are forming a octahedral void. Okay, and you can see one of them has apex of the triangle pointing upwards and other has apex pointing downwards like this. One has apex pointing upwards like this and other is having apex pointing downwards like this. Okay, so this is known as octahedral void. Yeah, you can see here. You can see here this is the octahedral void form. Yeah, this is the octahedral void form and this is the tetrahedral void form. Okay. Yeah, octahedral sides. These are octahedral sides which are clearly visible to you, but the tetrahedral sides are this thing: 3 below, 1 above. In octahedral, 3 above, 3 below. So how many number of voids are there in close packed structure? This is one thing which you need to understand, that I want to know how many number of voids are there in a given close packed structure. That depends upon the number of close packed spheres or particles we have. It depends upon the number of close packed spheres. Okay. So if I take, like, if the number of close packed spheres is n, then n is the number of close packed spheres, the number of octahedral voids generated is equals to n, and the number of tetrahedral voids generated is equals to 2n. Okay. So there are always double the number of tetrahedral voids as compared to octahedral voids. So this n representing here is the number of close packed spheres. So if you know the number of close packed spheres, you can calculate simply the octahedral and tetrahedral voids easily. Okay. So let's do some MCQs so that to make the things clear that we discussed till now. So we discussed about 1D, 2D and 3D packing. Okay. So even the 3D packing also we haven't discussed completely. We discussed that there are, if you place the second layer in a different fashion compared to the first layer, you are getting tetrahedral and octahedral voids. This is what we discussed, but we haven't discussed completely about the 3D packing. That I will cover in my next part in detail, but till then let's do some questions to test our understanding. Okay. So the number of octahedral voids in FCC unit cell. Okay, to know the number of voids, we have to know the number of particles. Number of particles in FCC unit cell, we know that the number of particles are 4 particles. Okay. So if the particles are 4, then octahedral voids are equal to number of particles. So we have 4 octahedral voids is option B. But if they ask you tetrahedral voids, then double the number of particles. So 8 will be the tetrahedral voids and 4 will be the octahedral voids. Okay. And second question is, second MCQ is, if the coordination number of an element in its crystal lattice is 8, then the packing is, okay, in FCC the coordinate number is 12 and in SCP the coordination number is 12, but in BCC we have a coordination number 8. I will discuss more about it, the coordination number, since we haven't come across HCP and FCC till now, and this FCC and HCP are 3D packings, 3D close packings, and I will also discuss why the coordination number is 12 in these two, but now just remember that BCC is having a coordination number 8. Okay. So next MCQ is, which of the following crystallizes in a BCC structure? BCC structure that is given by cesium chloride, where cesium is a bigger cation. So the cesium ion is going to be at the body center, and the chloride ions which are smaller are going to occupy the corner positions. So cesium chloride is having a BCC structure. Okay. So I will stop this part here, and whatever the remaining things about the 3D packing is there, that I will cover in my next part. Okay. So students, in this part we discussed about how we can arrange the spheres in 1 dimensions, in 2 dimensions and in 3 dimensions as well. So we first saw how we can arrange the set of spheres in 1 dimensions, right? So then we have seen how we can arrange the spheres in 2 dimensions. There we got the concept of the square close packing and hexagonal close packing, and then we moved on to the three-dimensional packing. So in that we placed second layer over the first layer, right? So then we got the concept of tetrahedral and octahedral voids. So we discussed about the tetrahedral and octahedral voids in detail, and we also calculated the number of voids, tetrahedral and octahedral, from the number of close packs spheres we have. Okay. So now we're going to discuss more about the three-dimensional close packings. So how we can place the third layer over the second layer. So to know more about the three-dimensional close packing, keep watching for my next part.